Hello viewers, welcome to my channel ITJ Olympiads and AP Physics with Ambarish. And today I've brought one of the most controversial questions from communication systems. It's an actual question from JEE Main 2013. It turns out that this question was out of syllabus. However, since they have asked it, so I have to present the theory regarding this, and I expect that maybe in future, since communication systems is getting into advanced, maybe these type of things would be expected even more and more. So that's why I decided to take up this question. So without much ado, let me straight away get into the question, and then I'll get into the required theory, and then finally we'll solve the question. Okay, let's see. So here's the question, actual question from JEE Main 2013. So let me read out. A diode detector is used to detect an amplitude modulated wave of 60% modulation by using a condenser of capacity 250 pico-farad in parallel with load resistance of 100 kilo-ohm. So this is the situation. Okay, so we have a diode over here, we have a capacitor over here, and we have a resistor over here. So how does the detector work? So you might have seen the rectifier circuit from semiconductors. It is somewhat similar. So when the diode is forward biased, the capacitor gets charged and then it gets discharged through the resistor, and how that leads to detection of envelope we'll see shortly. Okay, so this is our circuit, and what are we asked? Okay, so capacitor is 250 picofarad and the resistance is 100 kilo ohm. Find the maximum modulated frequency which could be detected by it. So we have to find out the message signal frequency, maximum allowable message signal frequency, which can be detected using this kind of diode detector circuit. Okay, so I'll get into the explanation right away. I doubt it very much. Most of you must not have studied the theory, the requisite theory, and some solutions are going around on the internet which are not correct, which are not based on sound understanding of the things. So let me present you the working and then entire explanation. Okay, so how does a diode detector work? So essentially this part is given in NCERT, although it doesn't explain anything, just tells what happens exactly, the schematic. So what happens, this is an amplitude modulated wave, it gets rectified when passing through rectifier, and then it passes through envelope detector, and the purpose of envelope detector is to just determine this envelope of the this is what we want to do. So how is it accomplished? So here is the detailed circuit, and now we'll focus on this circuit and most importantly on this graph. And now you need to pay very careful attention, and I'm sure you'll be able to understand the working of envelope detector. So what happens? See here, this is my message signal. This dotted line is the message signal that I'm interested in getting out. Okay, and what is it that I'm getting as amplitude modulated signal? What I'm actually getting is this kind of fast moving wave kind of a thing I'm getting, and from this wave I have to infer the dotted signal. Okay, that's what I want to extract. So what exactly do I do? So here is a capacitor. What happens when the amplitude modulated signal reaches its peak? This diode is forward biased. So long as the voltage of AM signal is more than the voltage of the capacitor, this diode will be forward biased, and then the capacitor will get charged to the peak. Okay, so as soon as the AM signal is about to hit the peak, this capacitor will get charged, and when the AM signal goes below the peak, then obviously this voltage becomes less than the capacitor voltage, and this diode gets reverse biased. So what happens, this diode is reverse biased, so no more current will flow from here, but the capacitor is already charged to almost the peak potential. So what happens, the capacitor will start discharging through the resistor, and what will happen, the voltage that I am getting is, this is kind of this part, it seems like a straight line, but it is actually basically e to the power minus t by tau type of discharging graph for the capacitor, right? So what will happen, this will discharge a little bit, and when the amplitude modulated signal again is about to hit the peak, once again the diode will get forward biased, and when the diode gets forward biased, it becomes conducting, and again the capacitor is charged to the peak of the amplitude modulated signal. Again it gets charged, and again it gets discharged, then again it gets charged. So this cycle keeps on repeating. So please pay very careful attention. I'll repeat once more what's happening. When the AM signal is about to reach the peak, this diode is on. Diode is on means diode is conducting, it is properly forward biased. Capacitor gets fully charged near the peak, and once the capacitor is fully charged to the peak voltage and the voltage drops, the diode becomes reverse biased, it becomes cut off. Diode is off here, for example, because it has crossed the peak. In fact, everywhere I could show along the slant lines here, these are the regions where diode is off. So capacitor is discharging, and once again it hits the AM signal hits the peak, again and again capacitor gets charged and discharged. So what I am getting is not exactly what I intended to get. What I wanted was this dotted line signal I wanted, and what is the AM signal? That is this zigzag kind of signal. But what I am able to retrieve using this RC circuit and diode combination is this graph. See this graph, this is the graph that I am able to retrieve. So now it's not a perfect job, but still it's a reasonable good approximation of the envelope. Okay, so this is the purpose of my envelope detector. Okay, now what will happen if I want to follow this envelope very closely? I would like to follow this envelope as closely as possible so as to retrieve the message signal as accurately as possible. Otherwise, if I'm getting some kind of a zigzag signal, again I'll have to do some processing to get the approximate this dotted line kind of signal. So there will be further signal processing required. Okay, so that is my aim. So to how to get the most accurate possible detection of the envelope. So for that you need to have some conditions on RC, values of R and C. You see, the product of RC, that is the time constant of discharging, that will determine that what will be the slope of this decaying lines when after the peak. The slope will be determined by the value of RC. Okay. Now what happens, suppose the product RC is very small, suppose this time constant is very small. What will happen? I'll show you this figure. A picture is worth 1,000 words, so I just skipped all those 1,000 words and straight away cut the chase to the picture. What will happen? See, if RC is very small, it will hit the peak, and then of course diode will get cut off, but then the capacitor will discharge almost immediately. So you wanted this to discharge slowly so that it is able to capture the other peak, the next peak, but instead of capturing the next peak, it is just drowning all the way to zero. So the capacitor will get almost instantaneously discharged if RC is very small, right? Whereas if RC is very large, that will create another problem. So again, suppose RC is very large. So for example, here it hit the peak, and then capacitor started discharging. But when the capacitor was discharging, it turns out the message signal peaks were all lower than the capacitor voltage itself, right? Capacitor was discharging, but even after discharging, the voltage of capacitor was always more than the voltage, the peak voltage of the AM signal. So that means what? The diode never got forward biased all the while. So you missed out all these peaks. Why? Because capacitor was already having more voltage than the AM signal, and diode was always reverse biased. All these peaks got lost. So we need to have RC in the Goldilocks zone. RC need not be very small, and RC cannot be very large. In both cases, we will not be able to accurately reproduce the envelope. So what we really want is RC should be just sufficient so that I am able to approximate this envelope as good as possible. Okay. So let me read out what I have written. Okay. So let's see. So when a new peak is about to appear in the AM signal, the diode becomes forward biased and the capacitor gets charged nearly the peak voltage of the AM signal. So I'm just repeating what I said in the words. Once the peak is crossed, the capacitor begins to discharge through RC circuit, and if RC is large enough, the voltage across capacitor decreases very slowly. RC should be optimally chosen so as to closely capture all the peaks. Practically, RC should neither be too low nor it should be very high, for the reasons I just now explained graphically. And as a rule of thumb, this is the equation that you will get in most of the communications textbooks, and I think some of the JEE literature also, they'll be having this equation. So what does it say? That the time constant of the RC circuit, this should be much greater than time period of the carrier wave, and this should be much smaller than the time period of the message wave. So all of you know that carrier frequency is very high, whereas message frequency is generally in kilohertz. This is generally in megahertz. So time periods are inversely proportional to frequency. So that's why I said that time period of the RC discharging circuit, it should be much greater than the carrier time period, and it should be much smaller than the message signal time period. But this much smaller than and much greater than, this sounds very vague. And in the present question we were supposed to find some good limit in terms of given parameters. So how to go about doing this quantitatively, that we'll see in the upcoming portion. Okay, so these are the two things I told you, that when RC is very small you just miss out the next peak, it just discharges, and when RC is too large you are going up above the so many peaks and you're again missing so many peaks, right? So to capture the envelope properly, the magnitude of slope of RC discharging circuit should be everywhere at least slightly less than the slope of the envelope, so that it may dig a little deeper below the peaks and not miss them. So what I mean by this, listen very carefully. You see, so RC is discharging, and when by the time the next peak hits, it is a little below the next peak, right? Again it is little below the next peak, again it is little below the next peak. We do not want that it should be above the next peak, otherwise those peaks will be lost. So little bit of digging is fine, but it cannot go above the peaks, otherwise I'll be missing the peaks, right? So therefore what should happen is the slope of this RC discharging should be greater than the slope of the envelope itself, right? Because peak to peak portion of the graph is has the same slope as the slope of the envelope. So I want that the slope of the RC discharging circuit should be slightly greater than the slope of the envelope itself, so that I can dig a little below the peak. Too much digging is also not good, because if it digs too much below the peak, then I do not know where the peak is, right? So again the message is lost. So I want it to dig as little as possible below the peak, but it should not pass above any peak, so as not to miss any peak, so as to accurately recover the message signal, right? So that's what I've written. So to capture the envelope properly, the magnitude of slope of the RC discharging circuit should be everywhere at least slightly less than the slope of the envelope. Actually it's a negative slope, that's why I've said slightly less than. Otherwise if you take the magnitude, it should be, in a simpler word, it should be steeper than the slope of the envelope, right? The graph of the RC discharging should be steeper than the slope of the envelope, so that it may dig a little deeper below the peaks and not miss them. Also it should not dig too deep so as not to miss the shape of the envelope, right? Now let us consider a standard single tone amplitude modulated wave. So what I mean by single tone amplitude modulated wave, so you must have seen this equation in NCERT. It says that the amplitude modulated wave is carrier amplitude plus message amplitude sine of omega mt time whole thing times sine of omega carrier times t. So this equation is directly reproduced from NCERT itself, and obviously this means that we are having a message signal which has only one frequency, that is omega m. But that's not how the signals generally are. When human beings speak, their voice has got all kinds of frequencies, typically 1 kilohertz to 3 kilohertz, you can say. This is generally used for speech signals, human voice signals. So you'll be having a mixture of so many frequencies, but just for easy understanding we are taking a simple case at JEE level. So suppose I have a single tone frequency, that is message signal has got only one frequency, that is omega m. Okay, so here this is the envelope of the total signal, and this is what oscillates very frequently, which causes this type of effect, right? And we are interested in the envelope part. Okay, so this is the envelope and this is the fast oscillating term. Okay, so this is I have separated. So envelope as a function of time is this, which can also be written as, if you take carrier amplitude outside, so inside you will get 1 plus a message divided by a carrier, which is nothing but modulation index as written in NCERT. So this is the equivalent to this, right? And what about the voltage across capacitor? So let's say at some instant you hit a peak where the peak voltage was, let us say E, and now the discharging has started. So what will happen to, let's say this is your t equal to 0 when you hit the peak. So this is t equal to 0, let us say. So how will the capacitor voltage vary with time? So this will be you can say exponential decaying circuit. So e to the power minus t by RC. So and if you use the expansion for e to the power x, and x is very very small, so if you take the first term, this can be approximately written as e into 1 minus t by RC, right? So approximation we are using here for ease of calculations, because we know that this RC is very very large as compared to these times, because RC is much greater than omega m, and the time period of RC is much greater than the time period of the carrier, and this peak to peak distance this is about the time period of the carrier, right? So I can always use the approximation expansion of the exponential. So this can be approximately written as E into 1 minus T by RC, right? So this so I'll be using this expression for this decaying curve, right? Almost a straight line, you can say. I've approximated using a straight line. Okay, so so this is your voltage across the capacitor, and then I'll talk about its slope. So what is the slope of this curve? And I actually need the mod of the slope, right? Because I just want to make it steeper than the slope of the envelope itself, right? So the derivative of this will be what? E by RC. In fact, it will be minus E by RC, but if I take the mod, so magnitude of the slope is E by RC, and this steepness should be more than the steepness of the envelope itself, right? So this should be greater than or equal to dE by dt mod, right? Because RC slope is steeper, so as to not miss the peak. Otherwise, it will be missing the peak if its slope is less steeper than the slope of the envelope itself, right? So now what is the slope of the envelope? You see, envelope you just can differentiate over here. So this is your envelope, this is your envelope. So if you differentiate, derivative of AC will be 0, and the derivative of this will be mu, and sin omega mt derivative will be omega m cos of omega mt, right? And this AC will be as it is, so that's what I've written. So it is mu AC omega m cos of omega mt. So this is the slope of the envelope. And now just put in the inequality. So instead of dE by dt, we can put this, and instead of the so what do we get from this? So okay, so E by RC, so E itself was AC into 1 plus mu into sin omega mt, right? So E, this is your E, so E by RC becomes AC into 1 plus mu sin omega mt divided by RC, right? So this is E by RC, and this should be greater than equal to dE by dt. So this is your dE by dt. So you put here mu AC omega m cos omega mt, right? So now you rearrange this. So this gives you RC should be less than equal to, so AC will cancel off and you take the cross multiply and take the terms from here to there. So RC will be less than equal to 1 plus mu sin omega mt divided by mu omega m cos of omega mt. Now this is the requirement on RC at any general time, but we want RC to satisfy this equation at all times, because we are not going to change RC product for every time. RC is resistance and capacitance values are fixed. So this equation should be satisfied at all times, right? So so RC should be less than the least of this product, right? Least of this value. RC has to be less than the least value of the RHS. So how to find the least value? So you see, you can just differentiate the whole thing with respect to time and put it equal to 0. So that means what? So anyway, mu and omega m are constant, so you just take the rest of it, take the derivative of this with respect to 0 and minimize. So if you do that, for minimum value, sin omega mt must be equal to minus mu, and if you put that, your expression will reduce to RC is less than equal to 1 by omega m under root of 1 minus mu square upon mu. So this is an important result. You can commit this to memory. This you have to commit to memory, and one more thing you can commit to memory is this equation, the heuristics equation, that is this one. This one also you can commit to memory. Let me put it in a rectangle. So this also you can commit to memory. Okay. So if it's just a qualitative question, mostly you will be using this equation, but if it's a quantitative question, this is what you will get. In fact, when you are saying that RC is less than equal to this, actually the equality is best, because that will miss the peaks by least possible value, right? Because equality means we are just optimizing the whole thing, right? So best is to use it equal to this, or otherwise if you want to dig a little below all the peaks, then it can be less than also. Okay. And if it's a complicated circuit, then accordingly you can see what should be the bound considering all the message frequencies, right? And if you just rearrange this equation, omega m should be less than equal to root of 1 minus mu square upon mu RC, and since we have to talk about frequency, so angular frequency needs to be divided by 2 pi. So 1 by 2 pi under root of 1 minus mu square upon mu RC. And in our question, mu is given, R is given, C is given, so we just need to put in the values now. So mu is 60%, that is 0.6, the resistance is 100 kilo ohm, and the capacitance was 250 pico-farad. So putting in these values, if you find out this expression, it comes out to 8.48 kilohertz, right? So now, but 8.48 kilohertz option is not there in any of them. So we have 10.62 megahertz, 5.31 megahertz, 10.62 kilohertz and 5.31 kilohertz. There is no 8.4 kilohertz anywhere. So which one is the best option? You see, this is out of this range and this one is also out of this range. You have, don't round it off. Don't think that 8.4 kilohertz means I should round it off to 10.62. That will be wrong, because then you will be again making this thing, you'll be missing the envelope. Okay, so it has to be strictly less than this value, and the only option that is left is then D option, that is 5.31 kilohertz. Okay, so that is option D. So that was my analysis of envelope detector. Hope you enjoyed this analysis, and this video would be useful for you for your JEE Main preparation. And if you did enjoy the analysis, please do give a thumbs up to my video, and please share this video as much as possible with your friends who are preparing for JEE through WhatsApp, Telegram, Discord, or whatever medium you use for networking with your fellow students. It's very important to share this video so that my channel can grow and I stay motivated enough to do new videos for you almost every day. And thanks a lot for watching this video, and most importantly, yes, if you've not already subscribed to my channel, please do subscribe to my channel. Hit that subscribe button right away. And as always, God bless you all. Thank you so much. Thank you.